Welcome to Maths with EJD. We're still talking about real analysis, and here we'll be focusing on epsilon-delta proofs versus numerical verification. Okay, we go straight to that and we see what we have there. So talking about epsilon-delta proofs versus numerical verification, the objective is to connect rigorous epsilon-delta proofs with computational approximations so that we can prove a simple limit exactly, then mirror the logic in code and stress test it numerically. All right. So basically, under the basic calculus playlist, I showed how to find limits and things like that. And there, most of it, the first rule, the rule of thumb in looking for limit is to substitute directly the value the variable is tending towards into the function, and then whatever, so that can determine if the limit exists. And in fact, it gives the value of the actual limit. But when we come to real analysis, we use the epsilon delta proof, which follows what we have in this in section 19.1, the minimal recap for the epsilon delta definition. And it simply says that let f be defined on a punctured neighborhood of x naught. All right. So we say that the limit as x approaches x naught for f of x is simply L if and only if. So this limit is actually L if and only if for all epsilon greater than 0, there exists a particular delta greater than 0 such that 0 is less than the absolute value of x minus x naught less than delta. And that implies that the absolute value of f of x minus L, the function minus the limit, the absolute value of the difference between them is actually less than epsilon. So that is the basic statement. So this is the basic statement for the epsilon delta proof, right? So if a limit actually exists, then this will also be satisfied. At the end of the day, what we now do is we get epsilon in terms of, we get delta in terms of epsilon, basically. And then there are two major mindsets here when we talk about this. Uh, we have two key mindsets. The first of all, we talk about the rigor. Of course, if you substitute number directly, you can just get an answer. But using epsilon delta, you have to follow the rigor that accompanies real analysis. So you construct or at least specify a delta that works for an arbitrary epsilon. And then we have for numerics, you test many x's for some chosen epsilons. This builds intuition but never replaces a proof. So a proof is more rigorous than just testing numerically. So let's look at this worked proof where we find the limit of 3x as x approaches to. Where we want to verify, right? So if I was doing numerical stuff, all I would just do is substitute 2 for x and 3x and I get 6, and then I'm good to go. But here, beyond just getting that 6, I want to establish that that is actually true using the epsilon delta construct. So the goal is to find a particular, we want to see given epsilon greater than 0, we want to find a delta greater than 0 so that 0 is less than absolute value of x minus 2. So the variable x minus the value towards which it tends is less than delta, implying that 3x, the function, minus the limit is also less than epsilon. And the easy way is we just prove that. So we have absolute value of 3x minus 2. So the deal is to start with this expression and end up getting x minus 2 in the center, so that at the end of the day, you get epsilon over something which will be equal to your delta. So here now we have absolute value of 3x minus 6. If you factorize 3, we get absolute value of 3 into x minus 2, and that is equal to 3 into absolute value of x minus 2. So if we ensure that 3 absolute value of x minus 2 less than epsilon, it suffices to say that, from here now you can divide both sides by 3, and you get absolute value of x minus 2 is less than epsilon over 3. So you now say x minus 2 in the center, but here, this is less than delta, whereas this is less than epsilon over 2. Epsilon over 3. So in essence, we can say that delta is epsilon over 3, simply. Then we can say 0 is less than absolute value of x minus 2 less than delta is equal to epsilon over 3. And that implies that absolute value of 3x minus 6 is less than epsilon. Hence, the limit of 3x as x approaches to is equal to 6 indeed. So it is not enough to know that the limit is 6, but we use the epsilon delta construct to establish that really it does exist. So the constructive takeaway we get from here is that for an affinite function, say f of x equals mx plus b at x naught, we get the absolute value of f of x minus f of x naught to be equal to absolute value of m into x minus x naught. like that, right? I mean, just like how we got 3 into x minus x2 up here, okay? Just like how we got 3 into x minus x2 here. So you have absolute value of m into x minus x naught. So a perfectly good choice it will be delta equals epsilon over absolute value of m, just like the epsilon over the delta, which is epsilon over 3 here. So the absolute value of m here is absolute value of 3, which is simply 3. So then in 19.3, given epsilon, can we return a suitable delta in the linear case now? So for an infinite function f of x equals mx plus b at a point x naught, we know from the proof that absolute value of f of x minus f of x naught is equal to absolute value of m into x minus x naught. So a valid choice is delta equals epsilon over absolute value of m, just like what we talked about previously. So below is a Python function that implements this rule. So what are we simply doing here? Uh, you know, what we are simply doing here is to say we define a function delta, define delta for affine. So it takes the value of epsilon and then it takes m. Of course, m is that thing we factorize out to get x minus x naught inside here. Then we also have x naught and then we have b like that. Okay, so talking about f of x equals mx plus b in that situation. So this returns a valid delta for the function f of x equals mx plus b at point x naught given epsilon. So for finite functions, we simply have absolute value of f of x minus f of x naught equals absolute value of m multiplied by absolute value of x minus x naught, so that delta can be epsilon over absolute value of m. So if you say if epsilon is less than or equal to 0, we raise a value error because epsilon cannot be negative. It can be 0 and it can be negative, right? Epsilon has to be greater than 0. So you raise value around and say epsilon must be positive, right? Epsilon cannot be must be non-negative, right? No, epsilon must be positive. Yeah, I think that's a better word to use. It cannot be 0 and it cannot be less than 0, right? So if m is equal to 0, that's this absolute value now. Then you say if slope is equal to 0, f of x is constant simply because m is 0. So slope is constant. So it means f of x is b. So limits in that case will be trivial and any delta would work in that situation. And then we can return float inf, and then we return epsilon over absolute value of m in that case. So for here now, if we now say example for f of x equals 3x at x naught equals 2. So what we just need to do is we copy out this one now. We print delta for affine. So this delta for affine. For the epsilon, we use 1 times 10 raised by minus 2. That's 0.001. Yeah, no, 0.01. Yeah, 0.01. That's 1 times 10 raised by minus 2 like that. Then m equals 3 because we have mx. So our m is 3. Then x naught is equal to 2. And then b is equal to 0 because f of x is 3x like this now. So if you do this now, we can get we can get epsilon over this, which is which simply is 0.0033. So up here now we got epsilon over 3. So since we took epsilon here to be 10 raised per minus 2 or 1 times 10 raised per minus 2, that is 0.01 divided by 3 now, and this is what we get. We get 0.00333 and so on. Now let's talk about numerical verification harness for the linear case. So we'll check that for random x with 0 less than absolute value of x minus x not less than delta, the inequality absolute value of f of x minus L is less than epsilon holds. And what do we expect here? All tests should pass. So all tests should pass that delta scales linearly with epsilon as delta is epsilon over 3. So this provides evidence but not a full proof, right? So and that takes us to the code. So we need math and random, which are all libraries that are embedded in Python so we don't need to install. So they are inbuilt libraries. Then we define the function verify limit affine. We take m, b, x naught, epsilon, and we do 10,000 trials. So L here is m times x naught plus b, like that. So this is us substituting the x naught into the function directly. That is our L, right? Normally when we take limit, we substitute the value towards which x is approaching, which is x naught in this case. We substitute it for x, and we have our m and our b, which would have been supplied here. So delta is delta for affine, and we get, so the delta we did before, so you take epsilon, m, x naught, and b. So if not, mat dot is finite delta, constant function, return true, and delta. Then we sample x uniformly for a symmetric interval smaller than delta and confirm that 0 less than absolute value of x minus x naught less than delta implies absolute value of f of x minus L less than epsilon. So for underscoring, for everything in the range of trials, right? We're taking 10,000 trials in this case. So we say R is random dot random. So we sample a radius in 0, delta, then random to left or right. So radius is R times delta in this case. So x is equal to x naught plus radius if random dot random is less than 0.5, else minus radius. So if x is equal to x naught, we avoid exact equality. Then we say x. So we now take x plus or equals 1 times it. So we take a very small value to ensure that x does not ever become like x naught, right? Then we assert 0 is less than absolute value of x minus x naught less than delta, and val underscore OK is absolute mx plus b minus l less than epsilon. If not okay, we return false or delta, and then return true delta if otherwise, right? So example, we want to check for f of x equals 3x at x not equals to the one we've been working with. So we now take different values of epsilon now. So for epsilon which is 0.1, 1 times 1 e raised per minus 1 is 0.1. This is 0.01. This is 0.001. And this is 0.000001, I believe. So, and then, okay, delta, you have verified limit defined. Put the value of 3, which is mx. M here is 3. B0, because we don't have 3x plus a constant. So the constant there is 0. X naught is 2. Take epsilon is epsilon, and we do 10,000 trials. And by the time we do the test, we want to see if the tests are passed. We already saw before that we should expect all tests should pass, based on given the conditions. So we run that now, and you see in a blow, we have for all the epsilon values, now you see we have 0.00333, and all the tests are passed here. So that means all the conditions are met in that regard. So we can also reflect rigor versus numerics in short bullets now. So rigor delivers universality. So if you use the epsilon delta construct, you have a generalized way of verifying limits, right? So rigor delivers universality. So one delta of epsilon works for all x, close enough to x naught. Numerics deliver intuition and diagnostics. They suggest how absolute value of f of x minus L behaves as absolute value of x minus x naught approaches 0, but cannot certify correctness for all real numbers. So you need numerics for intuition and the diagnostics, but you need rigor for generalization. And that is the essence of real analysis and some other abstract, pure mathematics areas like that, maybe like abstract algebra and all that. Then you have constructive proofs, which gives explicit delta of epsilon formulas, and that is easy to test in code. Then you have non-constructive or qualitative proofs, e.g. via compactness can prove existence without a simple formula. Numerics can still explore behavior, but don't replace existence. Then we come to 19.6, where we look at an extension, where we look at a more serious expression, like you have limit as x approaches 0 for sine x over x equals 1. So how do we establish this using delta epsilon? Of course, we know this is actually correct. Normally, if you substitute 0 directly, you have sine 0 over 0. And because of the 0 under here, it should be undefined. But then we have other ways of doing it. We can write sine x in using Taylor's series, and then the x can cancel out. Or we can actually use L'Hopital's rule. Differentiate sine x, you get cos x. Differentiate cos x, you get 1. Differentiate x, you get 1. So you have cos x over 1, which is simply cos x. And if you put 0 in cos x, that's cos 0, and the answer will be 1. So that's true. But then we need to prove it rigorously using the epsilon-delta construct. So the rigorous roots A, so you can squeeze via geometry or inequalities. And what do we do in that situation? For x not equal to 0. So if you take x not equal to 0, or which is near 0, so x that approaches 0, but it is close to 0, but it is not exactly 0. For x not equal to 0, near 0 in radians, one has that cos x will always be less than or equal to sine x over x, and that will always be less than or equal to 1. So as far as the x is not at 0, right? So in that case now, we have sine of the limit, since the limit of cos x as x approaches 0 is 1, so the squeeze theorem gives that the limit at x approaches 0 of sine x over x is simply 1. And of course, you can also go using the L'Hopital's rule. But because this one is sandwiched in between here, so we can say this is rigorous, but not yet delta of epsilon explicit, unless we also quantify how close cos x is to 1, right? So another rigorous root we can take is what we have here as b. So we have rigorous root b, which is quantified. So we have quantified bound, which implies explicit delta. So for all real x now, so we can say absolute value of sine x over x is less than or equal to, the other time. So here now we now have absolute value of x cubed all over 6, right? So absolute value of sine x minus x. What's basically happening here? I think it's that f of x minus the limit thing. Okay, but then this is just sine x minus x, right? Talking about quantified bound, and that is less than absolute value of x raised to power 3 over 6. And that is from Taylor's theorem with remainder or standard inequalities, right? So, since sine is an odd function, if we if we expand sine x, I guess we have come to that point where I may have to write, okay, yeah. So we have absolute value of sine x minus x. So normally we know that sine x being an odd function is equal to, I think it starts with x. Yeah, I think it starts with x. Okay, well, substitute x directly. Substitute uh using Maclaurin, for instance, sine 0 is 0. So that's 0 over 0 factorial. Then and then we differentiate sine x, we get cos x. Cos x will be 1. Okay, good. I think this is it. So x minus x cubed over 3 factorial plus x raised to power 5 over 5 factorial, and so on and so forth. So, the next one should be x raised to power 7 over 7 factorial. That is what x is. But if we use this now, so if you now say sine x minus x, so it means we are subtracting x from here. So this can go now. And if that goes, so we can then have that expression we have there. So because if since we are taking absolute value, so we can now take minus, we can take minus out, and we have absolute value of x cubed over 3 factorial minus x raised to power 5 over 5 factorial plus x raised to power 7 over 7 factorial, like that. And that is exactly why, so if we truncate this here now, if we truncate it here, we now have absolute value of x raised to power 3. 3 factorial is 6, okay? And that is why we have that expression we have on that page. So that is why this x cubed, absolute value of x raised to power 3 over 6 is coming from. So from Taylor's theorem with remainder of standard inequalities, then for x not equal to 0 now, we now say absolute value of sine x over x. That is if we divide through by x, okay? So absolute value of sine x over x now. So it's more like, so if you divide this through by x, we have sine x over x minus 1. Okay, and then so you now have this to be equal to sine x minus x all over absolute value of x, like this, and that is less than or equal to. So since we have absolute value of x raised to power 3 divided by absolute value of x, 1 cancels out, so we have absolute value of x squared all over 6. So we can now choose a delta so that absolute value of x is less than delta, and that implies that absolute value of x raised to power 2 over 6 is less than epsilon. So in that case, we can make a simple choice to say that delta of epsilon will be the minimum between 1 and square root of 6 epsilon. Okay. I think what is happening there is we have 6 delta equals x squared. Okay. We have absolute value of x less than delta. Since we are using that construct for limit, so we have absolute value of x minus 0 less than delta would imply absolute value of what do we have now? Absolute value of sine x. I think sine x over x here. Sine x over x. Okay, let me go back to see that now. Okay. Yeah, absolute value. Okay, this whole expression now is less than or equal to absolute value of x squared over 6. Okay, good. I think that's the deal. Absolute value of x squared over 6. So, so what this one should have been, right, is without absolute value of x squared over 6 is now less than epsilon. So if that is the case, we're simply saying that, hmm, so because this is the same thing as absolute value of x less than delta, so we are saying that now, mm, so if we can get this, want to get x out of this now. Okay, let me take this up. Okay, so we are saying that this is now absolute value of x squared. If you multiply through by 6, you have less than 6 epsilon. Then, if you take square root of both sides, absolute value of x here will be square root of 6 epsilon, like that. So, in short, we are saying that delta, so since this is absolute value of x less than delta, absolute value of x less than square root of 6 epsilon, so we are simply saying that delta should be something like square root of 6 epsilon. But it all now depends on, that is what the expression gives us. But then if this is if this is so we take this together with 1, as you see here. So we're now saying that with that established, we know delta of epsilon can be square root of 6 epsilon from that expression. So, but then the delta of epsilon has to be the minimum between 1 and square root of 6 epsilon. So then whenever 0 is less than absolute value of x less than delta, we can have that the absolute value of sine x over x minus 1 is less than epsilon. So now we get a delta of epsilon kind of expression, though it's not straightforward because we have to take it together with 1. So we have minimum of 1 and square root of 6 epsilon. So anyone that is smaller between 1 and 6 epsilon, we use that in that situation. Okay, so that's the rigorous root B. So the takeaway from here is that here the delta of epsilon is nonlinear, because there's square roots involved now, as I explained on the other page. So reflecting the cubic error term of sine x, which is approximately x. So we truncate at the cubic term, so that's why we have a cubic error term in that situation. Okay, so that's the second rigorous root. So let's look at okay, still the same thing, except that here, if you want to look at it from the lens of numerics using Python. So here we say Python for sine x over x, which is explicit delta of epsilon and test. So from the bound that absolute value of sine x over x minus 1 is less than or equal to absolute value of x squared all over 6, we can choose that delta of epsilon is the minimum between 1 and square root of 6 epsilon. So the Python function below encodes this explicit truth and verifies it numerically. So what we expect, the test should pass, right? Delta scales like square root of epsilon, which is which is larger than linear scaling for small epsilon. And that is good news. We can allow a relatively larger neighborhood while still meeting the error. So in this case, now we use two inbuilt Python libraries, math and random. So we define a function delta for sine over x. So that's sine x over x now. So which takes in epsilon. So for the inequality, absolute value of sine x over x minus 1 less than or equal to x squared over 6 for x not equal to 0. So we choose delta, which is the minimum between 1 and square root of 6 times epsilon. So if epsilon is less than or equal to 0, it will raise an error that epsilon must be positive, right? Epsilon cannot be negative. If not, the epsilon, it will be undefined. That expression, square root of 6 epsilon will not be defined. So then we return minimum of 1.0 and square root of 6 times epsilon in that situation. And then you define another function, verify limit of sine over x, taking epsilon and 10,000 trials. So numerically test whether sine x over x minus 1 is less than epsilon holds for random x with absolute value of x less than delta. So we now have delta is delta for sine over x and take the value of epsilon. So for all values in range of trial, so r is random dot random. So radius is r times delta, and then we have random sine, which avoids x equals 0. So we have x is radius. If random dot random is less than 0.5, else minus radius. So if x is equal to 0, because x should not be 0, so we have x is 1 times 10 raised to the power minus 16. So if absolute value of sine x over x, we need the math library to do sine x over x minus 1 is greater than or equal to epsilon. That will return false and delta. Otherwise, return true and delta. Then we can now do example checks for different epsilons. So for epsilons for this following epsilons now, that's 10 raised to the power minus 1, 10 raised to the power minus 2, 10 raised to the power minus 3, and 10 raised to the power minus 6. And we do the trial like we did previously. So I just run this and we get our results. So all the tests are passed for all the values of epsilon like that again. And then the values keep going like according to the epsilon we have. So next, we want to do a generic numerical delta searcher, all right, which is useful for arbitrary f. So if you have any arbitrary f, right, so we can do a generic numerical delta searcher. So below is a numerical routine that tries to approximate a workable delta for a continuous function f at x naught with target epsilon. So it shrinks a candidate radius until it observes absolute value of f of x minus L less than epsilon for many random points in the annulus x naught minus delta, comma, x naught plus delta, take away x naught, right? So because that's I think we said it was a perforated neighborhood or something like that. And what we expect in this case would be that for f of x equals 3x at x naught equals 2, empirical delta should be on the order of epsilon over 3, right? Then for f of x equals sine x over x at x naught equals 0, empirical delta is often comparable to or larger than the conservative theoretical minimum 1, root 6 epsilon. The warning here is that this is not a proof, it is just a heuristic explorer. Again, we use those two libraries, random and math, and we define a function, empirical delta, f, x naught, L, epsilon, then start 1.0 trials 2000, maximum iterations 40, shrink 0.5. So we keep shrinking until we get what we need. Empirically search for a delta. So we're looking for delta so that absolute value of f of x minus L is less than epsilon for many sampled x with absolute value of x minus x not less than delta, and x is not equal to x naught. So we have the parameters f is the callable function, the function that is callable, x naught is float, which is point of the limit, L is float, which is candidate limit value, epsilon is also float, which is target epsilon greater than 0, start is float, which is initial delta guess, trials is integer, number of random samples per delta attempt, maximum iterations is integer, that's maximum number of shrink steps, shrink is float, that's factor in open interval 0, 1 to shrink delta when the test fails, and then it returns OK, delta, that's OK is Boolean and delta is float. So OK is true if a delta was found at past. Delta is the last successful or final tried value. So if epsilon is less than or equal to 0, it will raise an error because epsilon must be positive. If start is less than or equal to 0, it will raise an error again, because start must also be positive, the starting value. If not, 0 is less than shrink, less than 1, raise value error. Shrink must be in that open interval. So this is to guarantee that we have a shrink that is between 0 and 1. So it's a factor that is shrinking. So it has to be a fraction always like that. So but it has to be a fraction between 0 and 1. I think that's a better way to put it. So you have delta, which is float, start. Then for all values in range, maximum number of iterations. For all iterations, in short, good is true. So for all values in the range of trials, you have add at random, all these things we've been doing before. And then so we do it for f of x equals 3x at x not equals 2, and the limit is 6. Theoretical delta is epsilon over 3. And for this other one, now we have f of x equals sine x over x, continuous extension at x not equals 0. The limit here is 1. Of course, we also have theoretical delta, which is minimum between 1 and square root of 6 times epsilon. And we have f sine x. So we define sine x over x and all that. And we try that out and we see, yeah, so 3x at 2 for epsilon is 0.01. Everything is successful. Even for sine x over x at 0, for epsilon, taking all these values. So all the tests are successful. So how do we use this now? So we can compare the empirical delta from sampling to your theoretical delta of epsilon. They won't match exactly because sampling is random and theoretical bounds are sometimes conservative, but the trends should actually align like that. So what to look for in the outputs. So for the linear case now, we saw that for the linear case, we saw that 3 for 3x, you should see delta is approximately epsilon over 3 from the explicit function, and the empirical search returns a similar scale. Then for sine x over x case, the explicit bound gives delta, which is approximately square root of 6 epsilon, which is capped at 1. All right. Anyone that is minimum between 1 and absolute. So this once this one, if this one shoots over 1, then we take 1. All right, because it is capped at 1. Empirical deltas may be larger because the Taylor bound is conservative, and that is normal. Then we have some uh, short reflection talking about rigor versus numerics. So the epsilon delta proof is rigorous, and then the numerical one is intuitive, yeah, and they have their place, right? Rigor answers a universal question. Rigor is for generalization. The epsilon delta construct is for generalization. So for every epsilon greater than 0, does a delta exist, and how can we exhibit it? So we follow that process like that. Numerics answer a sampled question. For these epsilons and this point, did the inequality hold? All right. And then when teaching or learning, numerics build intuition and can reveal the shape of delta of epsilon, whether it is linear versus square root versus any other form it takes. Then when proving, only the epsilon delta argument settles the matter for the continuum of points. So if you want a conclusive proof, you have to go the epsilon delta way. Numerics is just to test things out. Okay. So we can have some further extensions to what we've been doing. So we can have some further extensions. So ideas you can try next. So other functions with explicit bounds, you can try f of x equals x squared at x not equals a. So you can work from absolute value of x squared minus a squared. That's where it's tending towards. And that is equal to absolute value of x minus a, x plus a. And then you can trap x plus a by restricting x minus a to be less than 1. And then in that, you can then have f of x is equal to absolute value of x at x not equal 0. Okay, this is another one. So this is a function. This is another function. That's absolute value of x at x not equal 0. So this is Lipschitz with constant 1. And that implies that delta is simply equal to epsilon. But here we need to do more work to get the delta. So you can just finish up that. We have nonlinear but smooth functions like f of x equals e raised by x at x not equal 0. So you can use the mean value theorem, so which is Lipschitz on the small neighborhood, to get a constructive delta of epsilon also. Then you have numerical delta profiling. So for each epsilon on the grid, e.g. 10 raised per minus 1, 10 raised per minus 2, 10 raised per minus 3, and so on, you can compute both theoretical delta and empirical delta. So using the value you are given. So visualize or tabulate to compare. That is, expect empirical often greater than or equal to theoretical when bounds are conservative, right? So we have a bonus here. We have a comparative table generator which compares theory versus empirical. So we define function, compare delta for 3x. We take epsilon, a list of epsilons like we've been doing, and then we initialize this. We open, it's more like you're opening a bank account for rows where you're going to be appending those rows epsilons later. So for epsilon in the epsilons list, so you have the theory to be epsilon over 3, just like what we got when we were doing the proof. Then okay, then empirical. So we have empirical underscore delta, and then you say x is 3x. So you have 2.0, 6.0. Epsilon start is 1.0 like that. So 2.0, of course, is what x is tending towards. 6.0 is the limit when we substitute the 2 directly. And we have a list of epsilons, and then we start from 0. Then we have rows that append. So epsilon. So you take all of this and return rows. Then we also define this compare deltas for sine x over x. Same thing like that with all the necessary values that way. Okay, and then we have the epsilon grid 10.0 times raised to power minus k for k in range 1,6. That's 10 raised to power minus 1 to 10 raised to power minus 5. And then we print f of x. So we run this now and we see the results. So you can see f of x is 3, for f of x is 3x at x equal to. So all the conditions are met for f of x equals 3x and f of x equals an x over x. So we have the theory ones and we have the empirical ones. So for the theory ones, you see, the theory ones are idealistic. You get something more accurate. For empirical ones, when you substitute the value, for empirical ones, you get something close, but maybe some kind of difference. And then the test hold true. So for sine x over x, you have the theoretical and you have the empirical, like that. So some differences between them. So to wrap things up, um, for 3x, we see that the exact Lipschitz relation gives delta equals epsilon over 3. All right, using the rigorous epsilon delta proof. For sin x over x, an explicit Taylor remainder bound yields delta equals minimum, anyone that is minimum between 1 and square root of 6 epsilon. So if the square root of 6 epsilon is bigger than 1, we take 1. If it's less than 1, we take its value. If it's 1, 1, we take 1, right? So code code helps you to see how delta should scale and sanity check your algebra without pretending to be a proof. So it's just to check and it's not a proof. If you want a conclusive proof, epsilon delta proofs work best, but numerical values give you intuition. And with this, we come to the end of this interesting video about epsilon delta proofs, which shows us a rigorous way of proving limits, right? And then we have numerical ways of seeing how things go. Right. So with this, we come to the end of this video. Let me know how helpful this is for you. And if there's something you like to try out, feel free to let me know also. If you have subscribed already, thank you so much. If you have not subscribed, of course, you want to do that right away. And if having subscribed, you want to hit the notification bell so you can always get alerted each time a new video is released, right? And once you have done that, you want to take it a step further if possible by becoming a member of this channel. And that grants you some special privileges. And at the very peak of it, you may have opportunity to have a one-on-one conversation with me on anything that interests you on this channel. Here I talk about maths, data, anything, things related to data. I talk about scholarships, personal development, and different things like that. So you may want to have a hangout if you're a member of the channel at a particular level like that. Of course, ultimately, you want to comment, like, and share this video so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.